This video is part of a sequence on data representation. Instructions are a key part of any computer system. They tell the computer what to do. And instructions are stored in the computer memory just like all other data and represented as binary digits. And as you can see, we're still working our way through the layers of the computer system. We're still a fair bit down on the stack. We're now down at the point where the CPU has memory, has bits, and can represent numbers and characters. But now we're going to talk about representing instructions that the CPU will execute when it runs a program. Okay, now computer programs are actually a set of instructions that are executed by the CPU, and these instructions are stored in the memory of the computer. This was a great breakthrough in the development of computers, that instead of storing the instructions externally, say on a punch card or as a patch panel or wired in, you store the instructions in exactly the same memory as the numbers and the characters that you want to store and that you want to work on. So when you compile a language like a programming language like C, it gets converted into a set of machine instructions, which are just bit patterns in this memory, in the main memory of the computer. And the CPU will then execute these instructions, will interpret the bit patterns to work out what the instruction is and what the operands, what the subject of the instruction is, and will carry out the instruction using its internal logic. Now, the representation of instructions might look like this. It's just a sequence of bits, just like your numbers and your characters. And in fact, if you've got an error in your program, you might accidentally start executing the bit patterns that are your numbers. The raw memory makes no difference between the instructions and the numbers or characters that you stored. So this bit pattern I've got here is a made-up instruction. Let's say I've got a hypothetical computer, CPU, that interprets these bits as instructions. And this one might mean add the integer in address 4. Remember, our memory has memory addresses to be able to find the bit patterns you're looking for. Add the integer in address 4 to the integer in address 8 and store the result in address 12. And as I said, this is a really, really key idea. It's amazing it took so long for people to come up with this idea, that they should store the instructions in the same memory as the data. Perhaps it was because memory was very expensive, the different ways that memory was created, and there were lots of different technologies invented for storage, and all very, very expensive. Perhaps that was the reason that they thought, well, we'll just store the instructions separately. But once you have the instructions stored in the memory of the computer, you can do way more things, as you will see as we go along. So let's break down that bit pattern I had on the previous slide into its components, and we'll see how it's interpreted as an instruction. Now remember, this is a hypothetical computer. I just made up this instruction set, and but it serves to illustrate the mechanism. So the first 4 bits I've designated as the actual instruction code, telling us what the instruction is. And in this case, I'm saying that 0110 is the code for the add instruction. And then I've got 3 4-bit fields that represent an address in the memory, very small memory, and think of how many different memory locations you've got if you've only got 4 bits. And these designate where the operands and where the result is going to go. So the first one is address 4, the next one address 8, and the last address 12. So it tells the CPU where to find the numbers it's going to add and where to put the result. Now, there are many different types of CPU, each with their own unique instruction set. And the bit pattern I've given here for the add instruction is almost certainly not found in real life in any other real computer. because there are just so many different CPU architectures, different instruction sets, all with different bit patterns to represent the add instruction. Now, I might have a particular Intel manufacturer CPU, and it would have one particular code for add. I might have a different architecture, an ARM architecture, which has yet another bit pattern to represent the add instruction. Also, there are differences in complexity. You might find some CPUs have a very large number of instructions that do all sorts of very complex things. Alternatively, a simple instruction set computer or a reduced instruction set computer would have only a few instructions, and you have to make do with those and maybe combine many instructions to get the effect of one of the instructions in the more complex computer. The common thing, though, is that they all store their instructions as patterns of bits in the memory. Now, one other thing I should introduce now is a feature of central processing units that is a special sort of memory outside the main memory of the computer, but a very high-speed memory that can be accessed very quickly, very high speed, and these are called registers. And this is where we put intermediate results. So we might be adding up a lot of numbers, so we keep all the intermediate additions in these fast memory locations called registers. The registers are usually about the same size, or exactly the same size as an integer in the computer, and we can work on them with a special coding, a special address that refers just to the particular register that you want to work on. So here I've given you 3 instructions as an example. One that loads the contents of address 4 into register 1, and then adds the contents of address 8 to register 1. So you'll get the addition of what was in location 4 and location 8 left in register 1. And lastly, an instruction to store register 1 into memory location 12. Now, I've written here the instructions not as bit patterns, because that's quite hard to read and to get your head around. Instead, I've written it in something called assembly language, and I've which I'll say a bit more about later. But here I've written register 1 as R1 to indicate register 1, and it's probably say 4 registers, in which case you'd need 2 bits to designate the particular register. And so R1 probably has a bit pattern of 0, 1 in your instruction. Now, assembly language is quite important. It's a human-readable way of writing machine instructions, but it's also a very easy language, if you like, to translate directly to the machine instructions. So we might write the word load, and that will get translated very easily into the bit pattern 0110, for example. We write R1 would very easily translate to the bit pattern representing register 1, and so on. And so it's very easy to write a program that will take lines written in this assembly language and convert them into the machine code for the computer. And the program that does this translation from assembly language into the machine code is normally called an assembler. And you might, in other courses, write some assembly code and use an assembler for it. There's all CPUs generally have an assembler program. Now, there's one other sort of register, as well as the general purpose registers that allow us to store intermediate results in a very fast memory. There's another type of register which is useful when you want to access, say, arrays, or you want to have an offset into the memory from some address. And these are called index registers. And they make indexing through an array or moving through a list of things very easy, because they take a base address and then the contents of the index register to add those two together to produce the target address, and that's what you use for the operand. So by changing the index register, I change the target address. So I can step through an array, gathering the values or storing values into the array. So if you look at this diagram, I've drawn the main memory here in the center, and I've put an index register I1 on the left there, and an ordinary register R1 on the right, and my instruction load R1, comma 4, if it's using the index register, then it will add the number 4 to what's inside index register 1, and use that to find the particular address in the main memory to find the operand that is then put into register 1. So that's an example of how that works. Here is some real assembly language. This is assembly language that is used for an architecture called the Intel 386, which is a very old CPU, goes way back into the 90s, but it is still the base architecture for Intel computers. The 386 architecture and instructions are a subset these days of modern Intel. Intel is a computer manufacturer or CPU manufacturer for all of their CPUs. And I just thought I'd show you real assembly language. It's got some things at the beginning there which don't actually get translated to real machine instructions. They start with a dot or an underscore. But then the next lines where it says MOV and there's several MOV instructions, what they're doing is moving some data from one place to another, from a memory address, say, into a register, and the int is something which invokes something called an interrupt, which I'll say a lot about later in the course. And this little program here, what it's doing is setting up a couple of parameters in registers, and then calling the operating system to do something, and then exiting the program. And the something it's doing is actually running a hello world program, telling the operating system to send the string hello world, which you can see down the bottom there, to some external device. So this is just an example of what assembly language looks like in real life. So just to finish off, some history, a little bit of history about computers. So I've mentioned this idea of the stored program computer where we store our instructions in the main memory was a great breakthrough. And that actually happened, the first implementation of this happened back in the 1940s after World War II. There was a lot of interest in building computing devices. And the first one to actually run a stored program in its memory was done at Manchester University in 1948, and in fact it wasn't so much a real computer. They had some ideas of how to build a computer. They decided to build a small-scale machine just to try out the ideas. And so it was this small-scale experimental machine, and also otherwise known, they called it the Manchester Baby. It was going to be a baby computer. And the memory was very small. It had 1024 bits only, each of 32-bit groups. They called them words, not bytes. That term wasn't invented until much later. And there were only 8 instruction codes, so 3 bits for the instruction code. And the first program that they ran in 1948 had only 17 instructions. So a very small program, but it showed them that they could write, this would actually work. You could put real programs in the memory and have them do real things. And they went on to build a much larger, more practical machine, which was operational by 1950. And there are many other early computers that were invented around that time. Cambridge had in the UK, had the NeXT machine that was operational in 1949, and it was a real computer. There are many fascinating things about the technology they use. I might put into some of the other lectures. So just to finish off, this unit is all about instruction codes, and the idea being that you can take instructions and encode them as bit patterns, just like we did with numbers and characters, and store them in the main memory of the computer. Additionally, I introduced the idea of registers and index registers, which are memory, but they're very fast memory, and there's only a small amount of it, and generally they're addressed specially inside the instruction. And when you write machine code, you usually write it as in a shorthand that's more human readable called assembly language. And assembly language is then converted into the machine code.